Okay, now let's discuss about the second thing, which is how to compute the power law transformation function and histogram equalization. Okay, for this case, I will like you invite you to open. Okay, you go to our e-learnings, then you open this power law.m. Okay, I provide that code. Okay, before we explain this code, okay, I will like to remind again for power law transformation functions. Okay, let's go to our whiteboard here. Okay, this one I just copy from your slide. Okay, okay, actually the equation for power law transformation function, again I would like to remind the R there is a normalized R. Okay, the one that I forget to mention, S also, when you produce the S, when you apply this equation, S is actually a normalized S. Okay, so in other words, if you want to do hand calculations, if you want to use this power law transformation function, please make sure you convert into normalized R first to use this formula by having this formula. Okay, this one have been discussed earlier. And the things that I forget to mention in the previous video lecture is that after you compute this one, actually you are producing the normalized S. Okay, so in order for you to get your original S, then you need to multiply the normalized S or S head here with your L minus 1. Okay, so this actually happened, this is same goes to the Matlab code that we discussed later, which is this one. Okay, you can see this is the example of power law transformation functions. Okay, just forget about this one. This one is just to clear everything here and to close all the screen, so your screen is empty. Okay, for example, if you type CLC here, it will empty the screen here. And then if you put clear all, close all here, you will clear all the variables inside the workspace. Okay, the one that you want to see is actually this one. Okay, for example, I read my image here. This is the image. Okay, this image also has been provided in your e-learning. And then okay, it's better for me to use a meaningful variable. Let's say I convert this one into I put it as my R. Okay, this one is my R. Okay, and then you can see here, this is what after I read the image, and this is when you read the image. And then of course, when you want to do something because since we need to do some computation or the mathematical operation, which is the power law transformation function, then the best way or the good way, the proper way to do programming, since our image here is unsigned 8-bit integer, or you can have the value from 0 to 255 only, so that type is not sufficient for you to to compute something, because if you compute any unsigned 8-bit integers, then many things will lost there. Then the result that you get actually have been convert into the nearest numbers, nearest integer. So that's why, for the safety purpose, in general, if you write the programs, okay, before you do any mathematical operation, please convert that variable into doubles. Okay, so that's why in this operation here, I convert it into double, and at the same time, that's why we divide it into we divide the value with 255 for the purpose of getting our normalized R. Okay, so that's why this one should be R norm. Okay, I just put it R norm, so then it's more meaningful there. Okay, in this case we use the C equal to 1, and then gamma equal to 3, and then this actually, when after you apply, okay, this one should be R norm. Okay, I just change into meaningful variable. Okay, if you don't want to change it, just leave it there. You can just run the simulation, you will get the result. Okay, this one for the purpose of try to relate it what we have learned in our slide. Okay, so when you apply, this is the one that represent the power law transformation function. Okay, you just multiply C with R normalization and your gamma, and then this one is represented to the power, okay, to the power of gamma, and then you get the S norm, and then to convert back and to get your actual S, then you need to multiply your S norm with 255. Okay, in this case, because the intensity level resolution is 255. So we try to run this code. Okay, there's a errors there because I still, okay, this one I will like to use because you already changed there. This one should be our R. Okay, that's the output. Okay, same as the one that we use in the slide there. This is the same image that we have discussed in the slide. As you can see, by having the gamma which is more than 1, okay, then you can see that it can can tackle the image which actually in low bright contrast image. Okay, so that's why then you can vary this gamma. Okay, for example, let's change it into, how about 4? Okay, it become more and more darker there, but you can try to tune which one is the best. Okay, how about 1.5? Okay, it's not so good because still can see very bright there. But let's say you use less than 1, let's say 0.3. What happens there? Okay, so means that now, like I said, okay, when when we talk about the gamma which is less than 1, it will actually stretch the range of the dark side, or the lower value side. So it will stretch from the narrow range into the wider range, but it's actually will compress at the bright side. So that's why if you apply this one which is already suffered with very bright region, now it has been compressed that region. That's why you can see the output just there become more and more bright, and actually you reduce the contrast even more and even worse. Okay, that's why it is not suitable to use gamma which is less than 1. So in this case you need to use more than 1, because you want to stretch at the bright side, so it will convert the narrow range of the bright side into wider range. So that's why you need to choose a good gamma, but that gamma should be more than 1. Okay, so you can choose, and you can try to vary that one. Okay, another thing I would like to highlight is that you can see here, when I try to plot, I change back all the value, the output value here as into our unsigned 8-bit. Okay, previously when I want to process, I change into double because I don't want to lose any floating information, the floating number informations there. Okay, once I get the S there, actually S in the form of double, which is, if you click here, okay, if I just click here, okay, I cannot get that number because the number is in three dimensionals. Okay, but actually the matrix there is in floating numbers. So in order for you to display back the image, then you need to convert back into unsigned 8-bit, which is from 0 to 255. Okay, that's why when I ask you to do hand calculation, the final product you need to change into integers number. Okay, and the range is depends on the intensity level resolution. Okay, if you talk about this simulation, they are using the default intensity level resolution within 8-bit per pixel. So that's why any floating number that happen at this variable S, okay, it will convert into integers. So any value, let's say this value get negative number, it will convert into 0. If the value is more than 255, it will convert into 255. So that's why this practice should be should be done by you, okay, in your hand calculation, because we want to do the same behavior or same mechanism as what we done in simulation in Matlab. Okay. Okay, then again, that is the power law transformation function. You can see that is the disadvantage of power law transformation function. Now it depends on the situation. If you talk about this image, because this image is low bright contrast image, that's why you need to use the power law which is more than 1. Okay, but again, I would like to remind you, when the alternative way to make it more better to solve this kind of situation is by having the histogram equalization, because histogram equalization, you don't have to think about whether the image is affected with, you know, a situation of low bright contrast image or low dark contrast image, because the transformation function is automatically generated based on histogram of the image. So how to apply the histogram equalization? Okay, for let's demo that thing here. Okay, again, our input image is R. Okay, that's okay. In order for you to display the image histogram, okay, you can use this one, I am his. Okay, and then we know our input image is R because we already run this code, and then this is our R there. So if you enter, okay, this is your image histogram. Oh, because it display from the previous one. Okay, now let's I am show our image R, and then I want my another figure. I request another figure. I want to display the histogram of the image by using this function. Okay, this function also you need to use a figures there, because otherwise it will draw at the same figures that have been display the image R's there. So that's why I need to request a new figure to display this one. Okay, so you can see that this is the histogram of the image. Sorry. Okay, this is the histogram of the image, and then this is the this is the image. As you can see that of course this image is under the what we call as a low bright contrast image, because most of the histogram is occupy at the bright side there. Okay, you can see that the dark side there is empty there, so that's why this happens. So then if you want to apply the histogram equalization, you can use this function. Okay, you can let's say my output image, I want to okay, I just put S. Okay, the variable name is S equalize. S equalize, S equal is equal to okay, his tag. Okay, that is a function to perform the histogram equalization. Then you just key in your input image, which is our R. Okay, then I display it by using iron tool, which is better. Sorry, that is R. So how about IM tools S equal. Okay, this is the image. Okay, so of course this one is quite bad there. Okay, that is not because of the histogram equalization is not performed well, because this one is JPEG image. Okay, because JPEG image always suffer with some effect that related to what happened when they perform the compressions there. That's why you can see a red dot there. But however, if you talk about the surface where it's not cannot be seen clearly, especially this part and this part, here you can see a little bit clear. Okay, by applying histogram equalization. So meaning that that is the purpose of histogram equalization. It doesn't matter what condition from the image, it can be solved by histogram equalization, where the previous transformation function like power law, you might have a difficulty in determine what gamma to be used. Okay, I also have some other image you can demonstrate with this function. I think okay, this one. Okay, you can try this one, which is let's try this one first. Chapter 1. I think this one I've been shared in our e-learnings. Okay, this is one image, chapter 1 image. Okay, if you run the power law, okay, let's discuss about this image first. Okay, this image is saved in our F. So if I display that, okay, if from this function you can see that our input image is saved in our, or assigned to our variable F there. So if you see the F there, okay, it's a grayscale image, but now it's unsigned 16. So meaning that this image is not the normal digital image that you save in your computer, which is 8-bit per pixels. Okay, this one is I believe a CT scan image. Okay, so this is one of the example for CT scan image. That's why the intensity level resolution is 16-bit. So if I display the image, okay, let me display the image. Okay, you can see you cannot see nothing's there. You don't see nothing's there. Okay, but actually when you put the cursor, you see there's a values there. The intensity is 1000 something, but you cannot see. Okay, this is where actually if you plot the histogram of this image, okay, now it's not 0 to 255, it's actually 0 to 65 something. Okay, because the maximum L minus 1 is 2 to the power of 16 minus 1. Okay, so that you need to count it. But what I want to highlight is that this image is under the condition of low dark contrast image, because every pixel there occupy most of the pixel there, or most of the histogram occupy at the dark region. Okay, it's very white areas there. It's empty. There's no histogram at all. Okay, so by having this kind of situation, then again you can use a power law or histogram equalization. Okay, for this case, since we know this is happen, okay, then if we want to stretch the dark region, so if you want to choose the power law to solve this problem, then you need to choose the power law which is less than 1. Okay, so then let's choose one value which is less than 1. Let's say 0.4. Okay, one thing that I will like to highlight here, because this one is a 16-bit per pixel. Now L minus 1 is this one. It's not 255 anymore. Same goes to this one. Okay, you need to multiply with L minus 1. So if I run this code, okay, then you can see actually it's a cross section of your brain. Okay, from the CT scan image. Okay, now it's still not too good, then we can try to vary this one. Let's say 0.1. What happened? Okay, now it's become more and more better, okay, as compared to the original one. Okay, so now let's try the histogram equalization. Of course, you get your F and then S equalize. Just put, let's give some simple names, so easy for me to type. Just call it as SS, for example, and then his tag my F there. So I am told my S. See, as this is the result after you apply the histogram equalization, which is of course still not so perfect, but you still can, this is the best that histogram equalization can provide to you. Still you can see the brain as compared to the previous one, where you cannot see the brain at all. because that image is affected, or it's under the low dark contrast conditions. Okay. Okay, I just show you how to display by using IMShow, okay, which is similar to the IM tools again. Okay, then you can try another example, which is food. I think food is low bright contrast image. Then you need to choose the gamma which is more than 1. Okay, if I not mistaken, food image food dot jpg. Sorry, I think the food JPEG is just a low contrast, not bright, not dark. Let's test the histogram. Histogram is see, because this one, because before you perform anything there, okay, because the food now is not it's a 8-bit per pixel, so this one should be 255 and this one should be 255. Okay, let's try 0.5. Okay, this one you can try, let's say more than 1, let's say 4. Okay, that's the problem. Like I said, now I just test the image histogram. You can see that for food, the image itself is a low contrast image, but not going to the dark side or not going to the bright side. So it's very difficult for you to apply the power law transformation function for this case. So that's why for this case, it's better for you to apply the histogram equalization.